My name is Michael Bendazis. Welcome to Math 241, Probability and Statistics, online lesson number 8. Thanks for tuning in again. Okay, so last lesson we finished 6.1 and we talked about in 6.2 applications. So we talked about fair games, decision problems, inventory problem, and the Monte Carlo method for estimating the value of a definite integral. Okay? And so today we're going to finish 6.2, which is going to be one more example of the Monte Carlo method for estimating a definite integral. So we're going to finish 6.2, and then we're going to talk about in 6.3 the mathematical expectation of a function of a random variable. In the first section of 6.3, a function of a random variable. Second section of 6.3, the mathematical expectation of a function of a random variable, and in 6.4, we're going to talk about theorems on mathematical expectation, and 6.5, we're going to talk about the variance and standard deviation of a random variable. Okay? So we're going to get all this done, hopefully this lesson. Okay? So let's go. Okay. So, example 6.12, and in this example it's going to be the Monte Carlo estimate of the definite integral from 0 to 1 of e to the negative u squared over 2 du. Okay? And so that's the example. And so the solution is going to be, well, first phi of u is going to be the integrand of this function, which is e to the negative u squared over 2. Okay? Capital M is going to be equal to 1, little a is equal to 0, and little b is equal to 1. And so why is that? Because u, the input into our function, those u's range between 0 and 1. Right? And that's because the definite integral is taken from 0 to 1, and our variable is u. And so u is ranging from 0 to 1 here. And so little a is 0, and little b is 1. Now capital M is 1 because the upper bound for this integrand for those u values is 1. Okay? So e to the negative u squared over 2, e to the negative of u squared over 2 is decreasing. And so that means that when u is 0, you have a value of 1, and then it decreases. It decreases after that point. And so u equals 0 and u equals 1. The function is decreasing. This is the value of phi of u is equal to e to the negative u squared over 2 from 0 to 1. And so when u is 0, the value is 1, and then afterwards is decreasing. And so capital M is the upper bound for the value between 0 and 1, meaning, from here to here. And so capital M is 1 will serve as an upper bound for phi of u on this interval. And 0 will be a lower bound. Oh, wait, capital M is 1. So that's our capital M equals 1. Okay. It's an upper bound for the values of that. It's decreasing, and when u is 0, you get e to the 0, which is 1. Okay, so the definite integral from 0 to 1 of e to the negative u squared over 2 du is equal to e of x. And so the reason why it's e of x is because it's equal to that's because the integral from a to b of phi phi of u du is equal to capital M times b minus a times e of x, or well, so e of x. Yeah. So then, if a is 0 and b is 1, this step interval is equal to capital M, which is 1, times b minus a, which is 1 minus 0, times e of x. And so that tells us that this definite integral here is equal to 1 times 1 times e of x equals e of x. So this equals e of x. And so that tells us this equation. Okay, so this equaling this tells us that equation. And we can say that the definite integral from 0 to 1 of e to negative u squared over 2 du, that integral, is approximately the sum from I equals 1 to n of x sub I over n. That means the average value, that means in the experiment we had, this is 1, and then this is e. So this is the graph of phi of u is equal to e to negative u squared over 2 from 0 to 1. And so if we look at this, here's a shaded region here. This is not necessarily on the y-axis, it's just above it somewhere. Okay, that's the area underneath phi of u from 0 to 1. And so if you shoot an arrow at that box, that rectangle, a large number of times, and you record how many times it hits the shaded region, then this sum would be the total number of times you hit the target, and then you would divide it by the number of times you shot. Okay, so if you shoot in this rectangle 1,000,000 times and you hit the shaded region 1,000 times, this would be 1,000 over 1,000,000. Okay, and so that fraction of how many times you hit in the shaded divided by the total number in the rectangle is an approximation to the area underneath that curve. That's what this is saying. Okay. Okay, and so using the random numbers, there's a table in table 4, appendix B. Okay, that'll tell you, and so that will tell you if you take the definition from 0 to 1 of e to negative u squared over 2 du, that's approximately I equals 1 to 17 x of I divided by 17. That will tell you approximately how many times this will be, how many times you hit the shaded region. It'll tell you randomly if you're trying 17 times, this sum will be 15 out of 17, and so then that would equal 0.8824. Okay? Wait, sorry. Okay, sorry. You calculate this yourself. You get 0.8824, but then the value using the table. So our estimate using the Monte Carlo method is 0.8824. Then the table tells us, the table says it's 0.8555. And so it's close. So basically, I'm telling you that if you have this region and you shoot a target at it, 17, you shoot at this thing 17 times, you do the experiment, it hits it 15 times. So it's saying 15 over 17. This decimal is approximately what it should be by the table. Okay? Okay, and that's that. So that's the end of 6.2. And now it's the end of 6.2. We'll do the homework on pages 193 to 195. and it's going to be exercises numbers 1, 2, and 5. Okay? Good. Okay, so that's the end of 6.2, and this is the homework. Okay, so that's the end of 6.2. 6.3 is the mathematical expectation. Of a function of a random variable. Okay, so the mathematical expectation of a function of a random variable. Okay, and so in 6.3.1, we talk about function of a random variable. Okay, and so definition 6.3. Let capital X be a random variable defined on sample space capital S. Let little g be a real valued function defined for values of capital X, and so those values range are in a real number. Okay. So G is a real valued function defined for all possible values of our random variable capital X. The random variable G of X is defined on S as follows. For each little s in the sample space capital S, G of X of S is equal to G of X of S. Okay, what does that mean? So what that means is that G is a function where the input of G of X is a function, is the input is S. This is the set of outcomes of an experiment. And so if the input into this function G of X is an outcome of an experiment, the output of G of X is a function where if you input an outcome of an experiment, the output is, well, first, what is the value of X for that experiment? It's a real number. And then what does G do with that real number value here? It spits out its own number. And so G of X is a function. And so that's the definition, and then I'm just going to draw this machine diagram here. What's happening here is that G of X is a function that if you input the outcome of an experiment, little s, right? If you input that into your function, the output of that function is G of X of S. So the output of that function is G of X of S. And so what G of X of S is if you have, let me do it this way, if you take an outcome of experiments here, you write this outcome, outcome of an experiment, like that. You take an outcome of an experiment and you plug it into your function capital X, your random variable capital X. the output is a real number. That's x of s. Your outcome is little s, you input that into x, you get a real number, x of s. Take that real number and plug that into g. And the output is g of x of s. Okay? Okay, and so that's what's happening here. We take the outcome of an experiment, and we input it into our function g of x, and the output is well, okay, so you take your outcome of an experiment, you input that into a random variable, you get a real number. Take that real number value of x, plug that into g, and g spits out another real number. Okay, so let's see what this means. Okay, so example 6.14. Let S be the experiment of rolling 2 dice, and let capital S equal to the set I, j, such that both I and j are between 1 and 6 inclusive. Okay? So we're going to roll 2 dice, and I'm going to express the sample space as a set of ordered pairs. So the first member is from 1 to 6, and the second member is from 1 to 6. And they're both could be different, they could be the same. Okay? And that capital S, this set is going to be the sample space for that experiment. Oh, so capital S is the experiment rolling 2 dice, and let okay, and I'm just going to let that be the sample space. Okay. I'm going to change this to E. Sorry. I'm going to let capital E be the experiment rolling 2 dice, and let capital S be the sample space for experiment capital E. Okay. Let capital X equal to the sum of the 2 dice rolls. And so what that means is that X of I, j is equal to I plus j. And this is for I, j in capital S. Okay, so for any ordered pair in our sample space, you just take X of I, j as the sum of I and j. It's the sum of the 2 dice rolls. Okay, and so now I'm going to let G be the function G of X is equal to X squared. And this is for any real number X. And so what is G of X? That's the question. And what is G of X? Okay, so G of X of I, j is just G, and by the definition, it's G of X of I, j. That's by the definition on the last board. So by definition, G of X of I, j is just G of the real value of X. Okay? Well, X of I, j is I plus j, so this is G of I plus j. right? I plus j, that's x of I comma j. X of I comma j is I plus j. And so the input into g instead of x of I comma j is I plus j. So g of I plus j, g is a function where you take your input and you square it. So the input here is I plus j, and you're just going to square that. So you're not squaring I or j, you're squaring what's inside the parentheses. So what's inside the parentheses is I plus j, and you're going to square that. Okay? Here, you're taking the input x and you're squaring it. Here the input is I plus j. So I plus j is what you square, not individually I or j. And this is so this is saying that g of x of I comma j is equal to I plus j squared. And this is for any I comma j in your sample space, capital S. So if you choose any ordered pair in this sample space S, your set of outcomes, then g of x of I comma j is I plus j squared. Okay? And so for that g of x that we described, we may write x squared instead. Okay? So this g of x defined here, where g of x is x squared, we could just write x squared instead. And we could think of the random variable x squared. Okay? Right? Okay, so g of x is also its own random variable, and so thinking of the random variable x, you could also think of, instead of g of x as a random variable, you could just think of, in that example, x squared as your random variable. Okay, and then similarly, new idea, similarly, if g of x is equal to a naught plus a1x plus a2x squared dot 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 plus an x to the n, if you have that polynomial for g of x, then g of x can be written as a naught plus a1x plus a2x squared plus dot 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 plus a sub n x to the n. And so instead of thinking of g of x, which is that, you can, instead of thinking of the random variable g of x, you could just think of this polynomial as g. You could just say the random variable, that whole polynomial, this thing, as a random variable. Okay, given some random variable x. We think of this whole thing I circled as a random variable. Okay. Okay. So now 6.3.2 is the mathematical expectation of a function of a random variable. Okay, so 6.3.2 is the mathematical expectation of a function of a random variable. Okay, so first let's look at theorem 6.2. So that theorem is let x equal b, a random variable, with probability function f of x. Let little g be a real value function defined for values of x that are possible values of capital X, or random variable, or for an infinity, or for a real number x, right? So it might be possible that x is defined for all those numbers, okay? Okay, the mathematical expectation of the random variable g of x is the quantity, this is the number, e of g of x, which is equal to the sum over x of g of x f of x if x is discrete. And if it's continuous, this is equal to the integral from negative infinity to infinity of g of x f of x dx if x is continuous. Okay? So this is the mathematical expectation of the random variable g of x. So we have the expected value of random variable x, but given our random variable x, g of x is also a random variable with its own expected value. And so now this is the expected value of g of x for random variable x. Okay? This if x is discrete, that if x is continuous. And this is provided, continuing from there, provided the series converges absolutely. That's this series. And this is if x is discrete. And that the integral is defined. This integral if x is continuous. Okay? So if x is discrete, so this is equation holds, this is equal to this if x is discrete, provided that this series converges absolutely. Meaning if you take the absolute value of each term of the sum, if the sum of the absolute values of the terms is finite, then you can say that equation holds. And then this is equal to this if x is continuous, provided that this integral is defined, then you get that it's a finite number. You don't get infinity or negative infinity, or that it doesn't exist some other way. Okay? So this integral has to be defined as equal to a finite number. That's if x is continuous. Okay, and so that's the definition of the mathematical expectation of the random variable g of x, all of this. Okay, so now let's do an example. Okay, so example 6.16. Let g of x be the random variable of example 6.14. Find e of g of x. Okay, so g of x, let g of x be the random variable example 6.14. And so that was, all right, so that's the one we just did, right? Where g of x is x squared. G of x equals x squared. Okay, so the solution, right, to finding e of g of x is e of g of x is equal to, So now keep in mind, so that experiment was we rolled the dice twice. This was dice 1, this was die 1, and this is die 2. Right, and we record the top value on each dice, each die, and so we get I here and J here, and x of I comma j is equal to the sum of the values, and then g of x is equal to of I comma j is equal to I plus j squared. That was example 6.4. Okay, 6.14. So E of g of x, well, first off, our sample space is discrete. X is a random variable. Capital X is a discrete random variable. Okay? Capital X is a discrete random variable because in the experiment of rolling 2 die, there are 36 possible outcomes. 6 for the first die, 6 for the second, 6 times 6, 36 total outcomes, right? So there's 36 total outcomes of the experiment, and then, so that means that the sample space of our experiment, the set of outcomes for that experiment, is finite, and that's a discrete set. So we have a discrete random variable here, x, for that experiment, which is the sum of the dice rolls. That's a discrete random variable. Okay, so E of g of x, since x is a discrete random variable, we know that this is equal to the sum over all possible values of x, of g of x times f of x, and that's because x is discrete, and from our definition. So we have the definition, and because x is discrete. So we know x is discrete, and the definition of the expected value of the mathematical expectation for random variable g of x, right? Definition and x is discrete. So it's equal to this. And so now this is equal to the sum from x equals 2 to 12. And that's because the values of x is the sum of the 2 dice rolls. And so x ranges from 2 to 12, right? The sum, x is the sum. Or another way to think of it is the sum of the 2 dice rolls ranges from 2 to 12. 1 plus 1 is the smallest, 6 plus 6 is the largest, and the sum ranges from 2 to 12. That means the value of the sum x ranges from 2 to 12. So we're summing over all possible values of x, from x equals 2 to x equals 12. Everything in between is also valued. And so now we're going to take that g of x. G of x is x squared. That's x squared times f of x. And now you have to multiply by the probabilities of each sum. Okay? We did this before. If you take all the possible values of x, the sums, from 2 to 12, okay, so if you take each possible value of the sum of 2 dice rolls, then this is the sum of the 2, so this is the probability. I'll just write f of x, right? So you know what I mean? So f of x is the probability of any of these sums. So the probability of a sum being 2 is if each is 1, and it's 1 over 36. Probability of 3 is 2 over 36. 2 over 36, this is 3 over 36, this is 4 over 36, this is 5 over 36, this is 6 over 36, and this is 5 over 36, this is 4 over 36, this is 3 over 36, this is 2 over 36, this is 4 over 36, 36, 10, 15, 21, 26, 30, 36, good. Okay, so these are the probabilities of each of these sums when you roll 2 dice. Okay, and so we're taking the sum from x equals 2 to 12 of x, these numbers squared, times their respective probabilities. Okay? And so this quantity here, this sum, is equal to, starting at x equals 2, it's 2 squared times the f of 2, which is 1 over 36. Right? It's 2, when x equals 2 is 2 squared times f of 2, which is 1 over 36, plus now 3 squared times 2 over 36, plus 4 squared times 3 over 36 plus 5 squared times 4 over 36 plus 6 squared times 5 over 36 plus 7 squared times 6 over 36 plus 8 squared times 5 over 36 plus 9 squared times 4 over 36 plus 10 squared times 3 over 36 plus 11 squared times 2 over 36. Keep the way I do the parentheses the same. Plus 12 squared times 1 over 36. Okay, I'm just summing over the values from x from 2 to 12, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. For each value of x from 2 to 12, what x squared times f of x is. Okay? And so you find each of those 11 products and you add them, and this is equal to 1,974 over 36. And this is equal to 54.83. Okay. That's equal to 54.83. Okay, and so this is the end of 6.3. And then the homework for 6.3 is on pages 199 to 200, numbers 2 and 5. Okay, so homework page 199 to 200, numbers 2 and 5. Let's go right here. Okay, homework page 199 to 200, numbers 2 and 5. That's the homework in for 6.3. Okay. Okay, so that's 6.3. Okay, so 6.4 is theorems on mathematical expectation. Okay, so 6.4 is theorems on mathematical expectation. And so theorem 6.3 is if C is a constant, then E of C is equal to C. So if your random variable little c is a constant, if it's just always some, if the value of a random variable is just a constant, then the expected value of that constant is C. And so here's the proof. It's very easy. Okay, so the proof is that E of C, the expected value of C, which we want to find, is equal to C. Well, C times the probability that your random variable, which is C, is equal to C. Right? The expected value of a random variable is all the sum of all the possible values of it times its respective probability. There's only one value for this constant random variable, it's C. And so the sum is just has one term. And so that term is the value C, the possible values of C, times the probability that C is equal to C. That probability is 1. And so this is C times 1, which is C. And so what this proves is that E of C is equal to C. And so therefore we just proved this equation. And that proof is done. Okay? Theorem 6.4. Let A0, A1, A2, ... and be constants. If e of x squared dot 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 and e of x to the n exist, then e of a naught plus a1 x plus a2 x squared plus dot 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 plus a n x to the n, the expected value of that random variable, right? So we said that you can think of this as its own random variable a while ago. So now e of that is just, that's if all of these exist, right? If all of these expected values exist, and those are constants, then this is equal to a naught plus a1 e of x plus a2 e of x squared, plus continuing this pattern up to including the last term, a sub n e of x to the n. Okay, so the expected value of this random variable, which looks like a polynomial, which is a polynomial, but e of that whole thing that I underlined, squiggly underlined, is this. Okay, and now a corollary. If a and b are constants, little a and little b are constants, then e of ax plus b is equal to a times e of x plus b. That's straight from Theorem 6.4. Okay, and so we have that corollary there. So that's Theorem 6.4, and so we're now going to prove it, which will also prove the corollary. Excuse me, here. So we proved that theorem. Now we're going to prove the next one, this theorem here. And by extension, the corollary. So e of a naught plus a1 x plus a2 x squared plus dot 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 plus a n x to the n is equal to e of g of x, where I'm going to let g of x be this. I'm going to say that that's g of x. So we have a random variable, capital X, and g of x I'm going to let equal to that, which is itself a random variable. So e of g, that's e then of what's in the parentheses, which I call g of x. And so e of g of x is the sum over x of g of x times f of x by definition. Right? By definition of this guy, and we're saying that capital X is a discrete random variable. Okay? And so now we're going to look at this sum. Well, this sum is equal to the sum over x of what g of x is, a naught plus a1x plus a2x squared plus dot 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 plus a n x to the n times f of x. And well, that's what that's equal to is a naught and the sum over x of f of x plus a1, the sum over x of x f of x, plus a2, the sum over x of x squared f of x, dot dot dot, plus a sub n, the sum over x of x to the n of x. Okay, so if we just take this sum and I apply properties of the summation to this, I can think of this as the sum of summations where I move the constants out of the summation by another property of summation. Okay, so then, all that means is, so you're taking this plus this plus this, plus dot dot dot, plus that. And so this is equal to 1. This sum is 1. If you add up all the probabilities of any probability function, one of the conditions is that you add up all the probabilities, you get 1. So that sum is 1. A naught times 1 is A naught. So that's A naught plus, this is the expected value of x. So it's A1 times E of x. This is plus A sub 2 times this sum. This is x squared, and that's the expected value of x squared. Plus dot 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 plus A sub n E of x to the n. This sum here is E of x to the n. This sum is E of x squared. This sum is E of x, and this sum is 1. So that times 1 is itself. And so now that entire thing, that's what we want to prove. We want to prove that E of this random variable is equal to that. Okay? And so now the proof is done. We show that this is equal to that. And this thing I circled is equal to that thing I circled. And that's the proof of theorem 6.4. And the corollary follows right from that proof that theorem just proved, where n is equal to 1. So for theorem 6.4, when n equals 1, the corollary is that n equals 1. Okay. What is this? Okay, so now example 6.19. Let x be a random variable. Of example 6.2. Find E of 3 minus 2x and E of x plus 4x squared. Okay, thank you. Okay. So example 6.2. So in example 6.2, so in example 6.2, x is a discrete random variable, and its probability function f of x is equal to 1/3 for x equals 3 and 2/3 for x equals 9. Okay, and so we found that E of x is equal to 7. Okay, and so this is example 6.2. Yeah, there's only 2 possibilities of x, so it's definitely a discrete random variable. Okay. So we're going to find E of 3 minus 2x and E of x plus 4x squared from the theorem we just proved, theorem 6.2. Theorem 6.4. Okay, so solution using theorem 6.4, we get that e of x squared. So first I'm going to say e of x squared is going to equal to the sum or x of x squared f of x. And that's going to be 3 squared times 1/3 plus 9 squared times 2/3. So I'm going to just take each possible value of x and square it, and then multiply it by its respective. Square this, multiply it by its probability, square that, and multiply it by its probability. And those summing over all possible values of x is 9. X equals 3, x equals 9. Okay, so that's 3 plus 54, so that's 57. Okay. Now e of 3 minus 2x is equal to, well, e of a constant is a constant, right? So just as a reminder right here, remember that e of a constant is equal to that constant. And so what we have here is e of 3 minus 2x is e of 3 minus 2 times e of x. E of 3 is 3 minus 2 times e of x, which is 7. So this is 3 minus 14, which is negative 11. Okay? And now e of x plus 4x squared is equal to e of x plus 4 times e of x squared. E of x is 7, so that's 7. 7 plus e of x squared, which is 57, and that's equal to 64. 7 plus 57 is 64. Oh, sorry. Wait, no. It's 7 plus 4 times that. 4 times e of x squared, 4 times 57. So that's 7 plus 228, which is 235. Okay. This is 228. 228 plus 7 is 235. Okay, so that's the end of 6.4. And the homework. Pages 201 to 202. Numbers 1, 3, 6. Okay, so the homework is on pages 101 to 201 to 202, numbers 1 exercises, numbers 1, 3, and 6. And so that is the homework for 6.4. Okay, and so that's 6.4. So now that's 6.4, and now let's look at 6.5. 6.5 is the variance and standard deviation. I'm back. Okay, I got a very good job. The variance and standard deviation of a real variable. So 6.5, the variance and standard deviation of a random variable. Okay, so 6.5.1, definition of variance and standard deviation. Okay, so 6.5.1, definition of variance and standard deviation. Okay, and so this is definition 6.4. And so definition 6.4 is the variance of a random variable x with mathematical expectation mu, or expectation mu is VAR of x, minus of x is equal to the expected value of x minus mu squared, provided that the expected value of x minus mu squared exists. Okay, so definition 6.4 is the variance of a random variable capital X with mathematical expectation mu is the variance of x is equal to the expected value of x minus mu squared, provided that the expected value of x minus mu squared exists. Okay? Okay, so definition 6.5, the positive square root of variance of x is the standard deviation of x. Good. So the positive square root of the variance of x is the standard deviation of x. Okay. So, in other words, so in other words, the standard deviation of x that thing, the standard deviation of x is the positive square root of the variance of x, which means it's the positive square root of e of x minus mu squared. When you take the square root of something and you write the square root symbol, it doesn't mean you're considering two values. So for instance, if you take the square root of 4 here, this does not equal plus or minus 2. Because the standard notation is that the square root of 4 is the positive square root of 4, which is 2. And the negative square root of 4 is, well, negative 2. So if you write the square root of 4, it's not wrong, but the square root of 4 is saying you're taking the positive square root of 4. That's the convention. And so if you want the negative square root of 4, you write negative square root of 4 to be negative 2. And how that relates to this is because when you take the square root of this, if I wouldn't have to write a plus sign here. If I wrote nothing, it would be assumed to be the positive square root of it. But then I'm going to just write plus to make sure it's clear you're taking the positive square root of this, right? And so this is not two values. You're not thinking this could be plus or minus this and then plus that. It's only the positive square root. Once you put the symbol in it or once you put a plus sign in front of it. And if you want the negative square root, you write the negative square root. So this gives you one value, not two, the way I wrote it. Okay. And so that's the definition of the standard deviation of x. Okay. Okay, and so note the standard deviation of x, the notation for the standard deviation of x, the whole thing, is mu. I mean, not mu, sorry, it's sigma. Okay, and note that the notation for the variance of x is equal to that sigma squared. So if you want to talk about the standard deviation of a random variable, you can use the notation sigma. And if you want to talk about the variance of x, you could say sigma squared, because the standard deviation is the square root of variance, positive square root, so you could say it's sigma squared. Okay, and so those are the notations for the standard deviation and the variance of x respectively, sigma and sigma squared. Okay, so now that's done. Example 6.20. In example 6.1, so example 6.1. So in example 6.1, x is the outcome of a roll of a die, of one die, okay? And e of x is just 3.5, right? So it's just rolling one die. When you roll the die, there's a value at the top of it, and then what is the expected value of that experiment? It's of that random variable x is 3.5. Okay, so example 6.1, which is that example, the variance of x is equal to the expected value of x minus mu squared, which is equal to the expected value of x minus, so remember mu is the expected value, and so that's 3.5, so it's x minus 3.5 squared, the expected value of that. Okay, and the expected value of x minus 3.5 squared is the sum from x equals 1 to 6. These are the possible rolls of the die, right? Possible rolls of the die are 1, 2, 3, 4, 5, and 6. And so this die, you can have either the numbers 1 through 6 as the top value. So those are the possible values of x. And so the sum, right, is just going to be these values, which is x minus 3.5 squared, times the probability of each value, right? And remember that the expected value of a random variable is the sum over the possible values of x f of x. And so the expected value of x minus 3.5 squared so the expected value of x minus 3.5 squared is just the sum over x of this input here, x minus 3.5 squared times the probability of that. Oh, wait, okay, so then we want this e of g of x, the sum over x of g of x times f of x. So we're using this here. And so here the g of x is this. That's g of x. And so e of g of x is the sum over x of g of x, which is this, times f. Sum over x of g of x, which is that, times f of x. So the sum of all possible values of x, 1 through 6, of g of x times f of x, where this is g of x. Okay, and so then that's equal to then take each value, and so you have 1 minus 3.5 squared times f of 1, which is just 1/6, right? The probabilities of each roll is 1/6, and so this is 1/6 plus 2 minus 3.5 squared times 1/6 plus 3 minus 3.5 times 1/6 squared plus 4 minus 3.5 squared times 1/6 plus minus 30.5 squared. 9.6 plus 6 minus 3.5 squared times 1/6. Okay, and so we're summing over all values from x1 to 6, plugging in x there and there. 1, 2, 3, 4, 5, and 6. F of 1 is 1/6, F of 2 is 1/6, F of 3 is 1/6, F of 4 is 6 over 1/6. Okay, and so you multiply all these things and you add up those products, and you get that this is equal to 175 over 60, and this is equal to 2.917. Okay, so that's example 6.1, and we calculate the variance of this random variable, discrete random variable is 2.917. Okay, here's the next example. Okay, so example 6.12. Example 6.21. And that's the variance in example 6.4 is. So we're going to compute the variance of x for that example. And so in example 6.4, instead. Let's do example 6.3 instead. So in example 6.3, this is example 6.22. The variance in example 6.3 is the following. And so in example 6.3, x is a continuous random variable, and the probability density function f of x is equal to 81x squared for 0 less than x less than 2, 0 elsewhere. 0 less than x less than 1/3. Sorry, and then we found that e of x, the expected value of that continuous random variable, is 1/4. So that was example 6.3. Okay. Okay, so now in this example 6.22, we're going to find the variance of the continuous random variable in that experiment, in that problem, and it's e of x minus mu squared, and so then that's equal to e of x minus mu is equal to the expected value, which is 1/4 squared. And so what that's equal to is it's equal to the definite integral from negative infinity to infinity of x minus 1/4 squared times f of x dx. Right? So we know, as just a reminder, e of g of x for a continuous random variable is the proper interval from negative infinity to infinity. So g of x, f of x dx, provided the integral exists, is if the integral exists, and we also need, the integral has to exist, and x is a continuous random variable. Okay? So x now is a continuous random variable and the integral exists. This integral exists and x is a continuous random variable. And so now then this is equal to the integral from 0 to 1/3 of x minus 1/4 x squared. That's our g of x here. So our g of x here is this, and then times f of x, which is that, dx. Okay, so our f of x here is this, and it's for those only those values of x 0 elsewhere. And so you only have to integrate from 0 to 1/3, where g of x is this. This is g of x. So e of g of x. That's g of x. So g of x times f of x. Those values. Okay, so we're going to integrate that, and then you compute that def integral, and this is equal to 0.00417. Okay. Okay. Good. So, another topic, 6.5.2 is the variance as a measure of dispersion. So the variance is a measure of dispersion. Okay, so the variance of x is the expectation of the random variable x minus mu squared. So the variance of x is the expectation of the square of the deviation from the mean. Okay, so variance of x is the expectation of the square of the deviation from the mean. X minus mu is the deviation of any x value from the mean, how far away it is from the mean. And so we're squaring it. Okay? So the variance of x is what we expect the square of the deviation of the mean to be. Okay? Okay? And so then, therefore, from that, we can say that the variance can be thought of as a measure of dispersion. Okay, and so let's look at this picture here. Okay, so now if we take mu, which is the expected value, and this is the PDF. This is the probability density function of a random variable x, a continuous random variable x. Right? This is the probability density function. Okay, and the top peak of this curve will occur at the expected value. And so now if you look at mu minus sigma and mu plus sigma, and you look at the values of the PDF between here, so you look at this region, then 68.3% that 68.3% of the area lies underneath this curve is in this section, one standard deviation away from the mean, right? This sigma is one standard deviation away, and so if you move at most one standard deviation away from you, you could go sigma to the left or sigma to the right, and so you'd be ranging from mu minus sigma to mu plus sigma, and the area underneath the curve, this whole thing makes up 68.3% of the area, total area under the curve. And then if you go mu minus 2 sigma here and mu plus 2 sigma, then if you look at just this section, it'll add another 13.6%. And then if you look at this section, it's another 13.6%. Okay, and so we're almost going to be done with this video. And then if you look at mu plus 3 sigma and mu minus 3 sigma, then in this section here and here, you'll have another 2.1%. And here you'll have another 2.1%. Okay? And then the remaining little thing here, for not just this part, but going to infinity, that entire thing will be 0.1%. And this, independent of that, this section itself will be 0.1%. Okay? And so this is figure 6.3 in the book. And this is percentages of area under the standard normal density curve. So this is the standard normal density curve. And so these are the percentages of area for each region underneath the standard normal density curve. 68.3% here, and the other percents in those places. Okay, and so we're going to stop the lesson here, and look forward to seeing you next time.